Welcome to videos on plotting the Bode plot. So let us consider general terms that will be used, that will be coming in the open loop transfer function of a system, so that we can plot the Bode plot more comfortably. The terms are there is a finite pole which is having a time constant tau1. So there is a pole at the origin. So there is a repeating poles at the origin which is 1 over a square, and there are n number of repeating poles at the origin which is represented by 1 over s power n. And we can also have a finite 0 having its time constant as tau2, having a cutoff frequency which is equal to 1 over tau2. And we can have a finite 0 at the origin, and we can have a repeating zeros at the origin, and we can have n number of zeros at the origin. So this is two zeros at the origin, this is n number of zeros at the origin. So this is the representation of poles, and this is a representation of zeros in a open loop transfer function. Now let us consider a plot where we have a term like 1 over 1 plus tau1 into s. So as we can see now, so this is a finite pole with a time constant tau1. So since it is the time constant is tau1, so the representation of the magnitude plot of this pole which is having a time constant of tau1 will be a 0 dB line up to 1 over tau1 frequency. After 1 over tau1 frequency, uh, the magnitude will be minus 20 dB per decade. As you can see now, this is how do we write? So till 1 over tau1 we can simply write it on 0 dB line, so like this. Afterwards the slope is minus 20 dB per decade, that is after 1 over tau1 we will come down by 20 dB, you go by one decade, and we'll have this point and this point. Now we can simply join these 2 points, so now this corresponds to minus 20 dB per decade, meaning the magnitude plot of 1 over 1 plus tau1 into s will be a 0 dB line till 1 over tau1, and afterwards it decays with a slope of minus 20 dB per decade. Similarly, suppose if we have a finite 0 which is represented by 1 plus tau2 into s, where tau2 is the time constant of the 0, meaning so till 1 over tau2 which we are represented here as the cutoff frequency, so till that frequency the magnitude contributed by the 0 is 0 dBs, and the slope is also 0. After that the slope is plus 20 dB per decade. Now how do we write this plus 20 per decade? Is from this frequency of 1 over tau1 you go up by 20 dB. Now you can see here we are considering each unit as 20 dB. Now this is 20 dB up, and from this you can see now this is 3, next it is 30. So it's always logarithmic in nature, this 3 and you see the next 3. So this is 3 here, the next 3 happens to be 10 times of that. So this is one frequency, this is the next frequency where there is a decade of a ratio. So you're going up by 20 dB, and this is one decade. So if we join this point and extend the line, so this line will have a slope of 20 dB per decade, that is plus 20 dB. Here also we can see this in 1 over tau1, so this corresponds to actually 6 here. So this corresponds to 6, this is 6, then one more 6 is there, so this is another 6. Make sure that you are coming down by 20 dB going by one decade, so that you can able to write 20 dB per decade line, which is now negative slope because you are coming down from this point. Now similarly, so let us try to represent how do we write 1 over s term. So 1 over s term will not have a cutoff frequency. The slope is minus 20 dB per decade throughout for all the frequencies. It is interesting to note that so this term which is 1 over s will pass through this 0 dB line when the frequency is 1 radian per second. The key here is the representation of 1 over s is a straight line having a slope of minus 20 dB per decade. So this the slope is minus 20 dB per decade, and the important thing is that this line will pass through 0 dB when omega is equal to 1 radian per second. So that's what is this. and it is also written something like this. You can see 20 dB per decade is given by 6 dB per octave. So this is an equivalent term. So let us try to find out what is this decade and octave. See here, we are considering frequency f2 and f1. So let us consider this as frequency f1 and this is frequency f2. As you can see, f1 is something like 100, f2 is actually 10 times of 100, which is 1k. That's what's written here. If it is decade, we always write the frequency f2 is equal to 10 times f1. So that's why it is f2 is equal to 10 times f1. So at f1 we have a gain g1, at f2 we have a gain of g2. So the difference in the gain will be 20 dB if the ratio of the frequencies is 10 dB. So meaning to say, so we say it as 20 dB per decade. So there's a 20 dB difference between G1 and G2, and you can see there is a ratio of frequency which is decade. We write it as 20 dB per decade. Similarly, see, this is the same line having a slope of minus 20 dB per decade. So let me consider two more frequencies, f, y and fx. You can carefully observe this is fy, this fx corresponds to, this is, if it is 10, this is actually 20. If you actually take this fx is actually 2 times of fy. As you can see, since this is 10, so this happens to be 20 now. So corresponding to fy, okay, let me assume this as gx and gy, or gy or gx. Just have a look at the difference of gx and gy. Since each subunit is 2, so this happens to be 2, 4, 6. Meaning, if the frequency is having a ratio of if it has a ratio of 2, then the gain will have a difference of 6 dB. Meaning, a 20 dB per decade line is equivalent to having a 6 dB per octave. When it is octave, the ratio of the frequencies is 2. When it is decade, the ratio of the frequency is 10. That is, higher frequency by a lower frequency ratio is 10. Here also, higher frequency by a lower frequency ratio is 2. Whereas the difference in the gain is 20 dB, whereas the difference in this octave is only 6 dB. And it is true for n into 20 dB per decade is equal to n into 6 dB per octave. So this is true for both plus or minus. That is, assume that if it is plus 80 dB per decade is equal to plus 6 into 4 is, because 80 can be written as 20 into 4, so it is equivalent to 6 into 4, that is 24 dB by octave, dB per octave. So let us see the representation of various other terms, like we have 1 over s term and we have 1 over s square term. We have a term which is s there, and we have a term s square. I can surprisingly see, note one change. The origin frequency is now 0.01. It need not be always 0.1. This can be any frequency. This is 0.01, this is 0.1, this is 1. So it is interesting to see all the terms, that is 1 over s, 1 over s square, s square, are all passing through this 0 dB line when omega is equal to 1 radian per second. Meaning, a 1 over s term will be a line having a minus 20 dB per decade, and it passes through 0 dB line at omega is equal to 1 radian per second. Similarly, the term 1 over s square is a line with a slope of minus 40 dB per decade, but it passes through again omega is equal to 1 radian per second. It passes through 0 dB line when omega is equal to 1 radian per second. It is true for s also, but in case of s, the slope is plus 20 dB per decade. It again passes through 0 dB when omega is equal to 1 radian per second. If it is s square, it is plus 40 dB per decade, and it passes through 0 dB line when omega is equal to 1 radian per second. So these are the basic terms which will be dealing whenever we try to solve any transfer function. Now this we have considered in the previous video also. This is 10 divided by s into, we can see we have a constant term, we have a pole at the origin, we have two more finite poles, one is at 5, other is at 10 radian per second. We know the magnitude at the origin is due to the constant term, as well as the 1 over s term is also contributing. So we have this as 20 log of 10 minus of 20 log of omega org, that is origin. So omega origin is 0.1 radian per second. We end up with this as 40 dB. Different terms in the increasing order of their cutoff frequencies, their individual slopes. I can see since this 10 by s is there, since there is a 1 over s term, as we saw in the previous case, so 1 over s term is contributing a slope of minus 20 dB per decade. So that's why we wrote this 10 by s, which happens to be 1 by s. Of course, this in terms of uh, contribution of the slope, it is only the s term which is contributing, which is minus 20 dB per decade, and this will going to again contribute minus 20, but its contribution is starting only after 5, whereas the contribution of the third term will be starting at 10 radian per second. So before that, its contribution is 0 in terms of magnitude. So that's what we saw here. The magnitude at the origin is 40. You come down by minus 40 dB. So this will be going till this is minus 20 dB per decade till the first cutoff frequency is at 5. After 5, you can see the slope is now minus 40 dB per decade. You, okay, how do we go from 5 minus 40 per decade is? So at 5, you come down by 40 dB, go by 1 decade, try to join this point and this point. So you extend this till only 10 radian per second. So this is a reference line to indicate that this is a 40 dB per decade line. And after 10, you can see the slope changes to minus 60. We are coming down by 60 dB, going by 1 decade, and this is now minus 60 dB per decade. Of course, we can see the theoretical omega GC and omega PCs and their corresponding phases, magnitude, the corresponding phase margin, gain margin. So this is from the plot. You can see there is a slight deviation from the theoretical calculation, the plot calculation. It is supposed to be there because there is some approximation done in the plotting, because we are plotting a asymptotic plot. So let us consider this term where we have repeating poles at the origin, which is s square. Now let us see the you can see magnitude at the origin is now 20 log of 50 minus of 2 into 20 log. This 2 is due to 2 poles at the origin. So this 20 log omega is the magnitude. So omega over g happens to be 0.1 radian per second. So which results in a magnitude of 74 dB. And you can see the initial slope is minus 40 because it is a 1 over s square term. So resultant slope is initially minus 40, and you have a 0. You can see now the terms are placed with the increasing order of the cutoff frequency. You have a 0 at 10 radian per second. The individual slope of this 0 is plus 20. The resultant slope is now minus 40, plus of 20 happens to be minus 20, and we have one more pole at 100 radian per second. So after 100 radian per second, so there is one more pole introduced to the existing minus 20. So it is minus 20, plus of minus 20 happens to be minus 40. And of course we need to note that okay, there is a change in the magnitude at the origin, which is 74 dB, and the change in the slope, it is initially minus 40, then becomes minus 20, then again becomes minus 40. This is how it is happening. You're starting with 74 dB, you're coming down by 40 dB. You can see you're going by 1 decade. So this is 40 dB per decade till 10 radian per second. You can see this line is extended till 10. After 10, the slope has reduced to 20 dB per decade. This is the resultant slope. Now you're coming down by, so this is the resultant because there is a plus 20 dB added by this 0. Now you are coming down by 20 dB, going by 1 decade. Now you can see the slope has changed positively. This is minus 20. This was minus 40. Now this has become minus 20, and there is a omega GC happening at 7.5 radian per second. And you can see after 100, the slope is again minus 40. Now you can see we don't have minus 40 down here. So what I did is minus 40 is equivalent to minus 12 dB per octave. So I'm coming down by 12 dB, going by 1 octave, that is twice the frequency, that is 200 radian per second. So that's what we discussed in the previous slides. 20 dB per decade corresponds to 6 dB per octave, whereas this minus 40 dB per decade corresponds to 12 dB per octave. I'm coming down by 12 dB, going by 1 octave. Now that corresponds to minus 40 dB per decade. So that way we can comfortably write the Bode plot of different transfer functions.